So for the final example, OS, the covers from chapter 8 to chapter 15 from all the slides, and there's 3 parts to it in the exam. First part is key and definitions. It's the top. They have she's gonna have a word bank for us, and then we're gonna choose and fill in which one makes sense the most. Second one is multiple choice, like always, and the third one is like previous ones. There's 3 big questions: is Banker's algorithm, page replacement, and paging. I'll cover all 3 of them like at the beginning, and then we cover the other concepts แบบคร่าวๆ like later after this. So if we look at Banker's algorithm, right, like last time we did เนาะมันมีแค่3ขั้นตอนในการทำคือ Banker algorithm มันต้องดูว่าอย่างแรกคือ safe is it safe or not safe, right? So is it safe to proceed or should we reorganize the order of process? So อย่างแรกเลยเนาะคือเราต้อง find the availables from here, which takes the total instance resource ก็คือที่เขาให้มาตรงนี้ลบด้วย total allocate. So total allocate คือตรงนี้เราต้องมาบวกตรงนี้ด้วยกันมาก่อน so ถ้าเราบวกด้วยกันเนาะ so it's 2 3 2 1 this would be 6 7 8 this would be 8 and then this one would be 3 5 7 and 5. Okay, we add all of these up, we got the allocation, and then for the total instances there's 11 5 6 9 6, so we can just line them up. So it's 11 5 6 9 and 6 leave แล้วก็มาลบกันเป็น 8 3 5 7 5. Subtract them, we get 3 2 1 2. Okay, so this is the available that we have. Like at this moment, resources free is that much for each slot. So I'm going to put it here. 3 2 1 2 1. Now the need, second step is find the need, right? Find the need is just have the max minus the allocate. So for each row, just find take the max and minus the allocate. So for this one, it's max minus allocate. So 7 minus 0 is 7. 5 minus 1 is 4. 3 minus 0 is 3. 4 minus 3 is 1. And then, so now we compare. Actually, we can do this for the rest. Say, and go ahead and fill it in. After we find the needs, right? Next, we just ask ourselves, do we have enough resources for each? So if this is available and you compare it to need, this one has to be greater than need. If is 3 greater than 7? No. So it's not enough. It cannot allocate. Otherwise, it will cause a deadlock. And so we have to skip this one. Skip to the next one. Check. We see. Is this enough? Compare. 3, 1, 2, 2 is fine. 1, 2. Oh, it's not fine. This one's greater than available. So this one cannot work as well. 6, 3 also not work. Hello, Poon. 6 and 3 doesn't work, so skip that one too. But however, this one works. And so if this one works, then we can allocate to here. And once this is allocated and done, these stuff here is gonna return back to here. We gotta add these ones together. So you see here, if there's enough space, we just add available and allocate together. So then this would be 5, 3, 2, 2, 1, because 3 plus 2 is 5, 2 plus 1 is 3, 1, 1, 2. Okay, so this is the first one. This is the first stop we have to take. Next one, we just check does this fulfill this one? Nope, it fails on here, 3 and 2. So skip that. Skip that to 5. This one is not enough for here as well. So we skip that, we go back up again, check. So now we have 5, compare this to this. Nope, doesn't work. How about this? Does work. So this one will be our second stop. So start off here. We looped around. This is our second stop. So we add this with the allocate. P1. Get 7. That's 2, 7, 3, 2, 2. Like that. And then next we move on. Down next one. Okay, now this one works as well. It seems like. Add that up. And leave 2. And this will be our third stop. Next one we jump down to here. That's fit. So 10, 3, 6, 4, 4. And last one is not last one. I'm sorry. Skip this. Fourth stop. And this would be fifth stop as well because this one is enough. 11, 4, 6, 6. Add this with 5. Now, finally, last one, just add here. End it off on here. Don't have to write it here because we're done. Now, first question is safe? It is not safe because it failed. And so we have to reorganize the orders. And so the process sequence is there. It's P1. No, it's not P1. It's P3 first, P1 next, and P2. P1, P3, P1, P2, P4, P5, and P0. That's the order. That's the first question. It's Banker algorithm from the previous midterm. That didn't appear. Second one is address mapping. This one is just converting this logical memory into a physical memory given this part here. So how do we start? Well, firstly, we calculate we need to understand that there are the components of this diagram. So like in this case, we have given n equals 2, m equals 4, 32 byte memory and 4 byte pages. What does this mean? 4 byte pages means that there is in a logical memory, there's 4 bytes per page. Okay, and in order for us to convert into a physical memory, we have to figure out how much does it need. But since we're given 32 here, we can see that if there is 32 bytes total, and there's 4 bytes each, we can see that there's the total frames, the total pages. Well, this one is called frames. So I was gonna say frames is 8 because it's 32 divided by 4. Right? So there are 8. Since we're given 32 here, memory for the physical, we're just gonna write 8 of these, right? So we can draw it there. But one thing to note that page size is equal to page frame. So if the pages here are 4, then here will be 4 as well. Okay, so now let me list them out. So this one is page number 0, so page number 2, 1, 2, and page number 3. Okay, so there's 4 pages in the logical address space. So how do we draw this diagram? So just draw the same 32 bytes in total, and each one is 4 bytes, right? 4 bytes, and it makes up a total of 8 frames, like calculated. So now the question is, where do we place these 8? There's four pages. Where do each of them go in the physical memory? Well, we look at the table. It tells you like directly that 0 here represents the page, and the 5 here represents the frames. So page 0 goes to physical 5, frame 5. So down here. So there we go. We just put these information in order 5. So 5 will become A, B, C, D. As we look at next one, it's 1, 6. So page 1, this content goes into frame number 6. It's down there. So it's E, F, G, H. Next is page 2 goes to frame 1. Page 2 would be I, J, K, L. And page 3 goes to frame 2. So then it's M, N, O. Okay, and this is the easy part. The trick question is the professor will come up with a question to translate. Find out how do you find O in the physical memory. In order for us to find the physical memory, we have to understand this concept. So the way data is stored in this form, in this context, is it's divided into 2 chunks. First one is page number, and this one is page offset. And in order to find the size of it, it's m minus n, and page offset's n. So m just now is 4, right? So 4 minus 2, and n is 2. This would be 2, so it's 2, 2. So this would be 2 bits for a page, 2 bits here. Don't worry much about this because if you look closely at the logical memory, it kind of makes sense because there's 16 rows here, 16 bytes, and 1 byte is 4 bits. So there we go. So we got this concept down. Now what we have to do is we need to find, let's say, it gives an example. Bun, give me a letter from in this here.
From where?
Here, any letter, pick a letter. B. So B. How do we get B in here? How do we find it in here? Let's see. Well, first off, we have to convert B into binary. So B has 1. What is 1 in binary here? So it's 1, 2, 4, 8, right? So then it will be 0, 0, 0, 1. Okay. So in binary, it would be 0, 0, 0, 1. Now, we got this now. Okay, now we have to convert this into physical memory. In order to convert this into physical memory, we have to remove this part. Here's the part. We have to remove page number and replace it with the frame number. Now, we have to look at the page table. Page table can be divided into 2 parts. This one is these are the pages, these are the frames. So let's see, there is 4 pages in total, and each page is, in order to store the number of pages, it's 4, right? So how many bits do we need to store for 4 pages? We need only 2, right? So only need 0, 0, 0, 1, 1, 0, 1, 1. And as for frames, we have, in total, we have 8 frames. So 8 frames. 8 frames needs 3 bits, right? So 5 would be 110, this one would be 116, 001, and 01. Okay, so this part is so what we did just now was B, right? We chose B down here, and then we put it in binary. Next, what we're going to do is we're going to replace the first 2 bits with the frame, and we got to match it. So you notice this is page 0, right? It's under page B is in page 0. So we go to page 0. It belongs to frame number 5. So we replace it with 1110. This is put it down here. There will be 110 and last 2 will be the same. Okay. Now where exactly in computer terms, where exactly is this? So we just convert this into decimals. 1, 2, 4, 8, 6. We add them up. 16 plus 8 plus that would be 425. I believe it's 25. So let's see. Number 25. No, I'm wrong. I'm sorry. What? They did the math wrong? Oh, my bad. Sorry. I'm very slowly. Thinks. Alright, 1, 2, 4. Yeah. My bad. So it's this, and then it's 4. So that's 21. 21 lies in 21 position. So where B is. So in the exam, she might ask how you translate that. Just show her how you replace them, and there you go. Because the computer cannot see this graph, you have to break down into binary to see it. So that's how you translate from logical to physical. Next one is drawing page frames in order. So there's 3 page frames. We don't know which one professor's gonna bring in the exam, but to be safe, I'm going to cover all 3 types. So first one is first in, first out. So imagine that this is like a room, right? And then people who is like Q box or whatever you want, imagine it as. And when people come in and out, if the number repeats, then no one has to leave. But if there's no number inside that exists that is the same, you have to find someone else. So start with 7. So when 7 comes in, there's no one that's 7. So 7 has to fill in. And then when 0 comes in, there's no 0. So then it fills in. It's first in, first out. So these guys come in. Next is 1. So then it's 1 here. Now 2. We gotta see. Is there 2 here? No, there's no 2. So replace the guy who first came in. So go. 0. 0 is in here. So we can skip this. Okay. Next is 3. There's no one in 3. 3 doesn't exist in this box. So we replace 0 because 0 is one of the first ones. Next is 0. So it's 2, 3, 0. Next one is no 1 doesn't exist. 4, 0, 2. There's no 2 in here, so it's 4, 0, 3 doesn't exist. 4, 2, 3. Put 3 inside. 0, none, so it's 0, 2. Now 3 exists. Okay, cut this out because there's 3 inside. Now 0 inside. Okay, what about 2? What about 3 again? 3 again is also now 2. 3 exists. 1, so this replace the one who came in like most least the first one. Next one is 2, so then 0, 1, 2, and 0 exists. I'm not gonna cover every single one of them for every algorithm. I'm just gonna show this in an example. 1 is 7, 7, 1, 2, 7, 0, 2, and 7, 0, 1. Now we can count if the question asks the number of page faults. How many page faults exist in here? We'll just count the amount of boxes that are here. Let's count 3, 4, 12, 13. Oh, there are 15 page faults in total for this one. Okay, that's it. Next one is finding the optimal algorithm. This one is it's called optimal for a reason because it's the perfect one. It sees the future and sees which one is used the most least. So allow me, I'm going to fill in these ones first. Now, when we get to here to see which one we should replace, once it's full, I'll draw you a way of. So we can see here which one occurs. It checks the future and sees which one is not going to be used the most. So we can count. So when will 1 be used again? Let's see. We can count. So 1, 2, 3, 9, 11, 13. And for 0, it's 1 and 2 because it's here. And 1 will occur again in 13 times. And 7 would occur in 1, 2, 3, 5. I lost track. But this one clearly isn't used the most in this set of data. So it's getting replaced. So replace it too. And the same process repeats. So same process repeats. 0 occurs. Okay, no need. It exists. What about 3? And now we look. So it's 1, 0, 2. 1 occurs in 1, 2. 0 occurs. 1, 2 occurs. 1, 2, 3. So 1 is getting replaced. And right, you know the rest. The rest is the same. It keeps on checking the future and compares which one has the most. That's it for optimal. As for the third one, last one, is least recently used. Instead of looking in the future, this one looks back into the past. So it sees which one it needs to be replaced, which one is used less often. 1 here, 0, 2, while 7 came in first, so gets replaced. S, it's 3 now. Go back and check past. It's 2, 0, 1. 2 was used here. 0 was used here. 1 was used way over there. So 1 gets replaced because 1 hasn't been used the longest. So then it's 2, 0, 3. Check it again. 0. It's 0, 0, fine. 4. Now it's 2, 0. 0 has been used here. 3 has been used 2 times. And 2 was used 4. 2 is getting replaced. 3. And so on. So that's least recently used. So all these 3 questions are the big questions that are 100% going to appear in the exam because she said it so. And after this, I'm going to fly through the concepts of OS from chapter 8 to 15. So yeah, I'm going to base this off my cheat sheet. So whatever it is I'm going to cover, you can refer to my cheat sheet. So first one is main memory. Main memory is just the address you store it's cut into 2 parts. There is logical and there is physical. Logical address is it's not in memory, but physical is stored in actual like long-term storage. So this is more like temporarily, while physical is like more permanent. Okay? And yeah, there are many ways to like protect the address. There's a thing called address protection where it checks two-step. It checks for if the address is equal to the address that they are looking for, and checks if it doesn't exceed the capacity, exceed the limit. In memory, usually storage is limited. So in CPU, it's limited. So whenever the CPU is full, say this is the memory. Whenever it's full, there's too many things inside. It's gotta start what it calls swapping. So swap once the threshold is exceeded, threshold of like capacity. Swapping occurs. It just moves the stuff out, and when it's ready to use it again, and this one is complete, the memory returns it. That's for memory allocation. As for allocation, like giving space, allocation is giving space into your storage. So let's say our storage is kept in like a grid like this. So if some parts are full like this, we don't know. And sometimes when application closes, they leave holes in the memory. And so sometimes holes are big, sometimes holes are small. They come in different sizes. And so there's 3 types of allocations that you can allocate. First one is first fit. First fit is, let's say you have a box. So whatever you come across, you just go in. That's first fit. And second option is best fit. So it finds the least it takes up, so it doesn't fits here, and it's better for optimizing. But it has the smallest leftover holes, but it takes time to for it to analyze the entire storage and find a spot like that. And the third one is worst fit. Worst fit is putting it into the largest possible hole, which it's called worst fit for a reason. So there you have it. There is a part that it might be on the exam. So we have to calculate the effective access time for the memory. So when memory exchanges, we need to know how much time it takes. So this is a CPU, and it doesn't want to go far. So it goes to the what's called a TLB, which if it's a smaller storage and it saves time. But if it doesn't find it in TLB, it has to go to the main memory. Now we're trying to find the amount of time it takes to find objects in each one to see if it's effective or not. So the formula for effective time is time it takes to access the TLB times the percentage that it hits. We covered this last semester, I think, for ComApp. She added it again. So this TLB at time access, if it missed, meaning that it has to go all the way to the memory, the time it takes for a CPU to go to access memory times the percent miss. And this one can be broken down into to find TLB normally is the time for accessing TLB plus the time it takes to go to main memory. Because it's quite complicated. I'm just gonna skip the complications. But for TLB miss, it's TLB, time it takes to access TLB, plus time it takes to access main memory twice. So does it 2 times. The penalty of missing it does it again. So that's how you find effective access time. I have it in my cheat sheet. I put a star on it. If you find it, feel free to just look at it. Yeah, and there's many types of page architect, which not that significant. Next chapter is chapter 9. I promise the first few chapters are a bit long because it's more concentrated here, but I promise that the later chapters is just gonna fly because it's very surface level information. So chapter 9 is virtual memory. Now virtual memory is memory that's created inside the CPU, and it's not permanent storage. It's not permanent, like I said, it's temporarily and temp storage. And whenever there is, so this one is related to the one we did just now. It's the page replacement thing where it has to swap things in and out. When from the example I gave just now, like these are the boxes, right? When at the beginning of every cycle, if the pages are empty like this, and then you have to fill it in, like 701, and then this is 770 These are page faults because it fails to find the same data. So if it's 7 here, then it's not a page fault. But if it's like a 9 here, then it has to be replaced, right? For example. So there are many types of ways to manage this storage, from checking if it's full or not full. There's like having like I said, page fault here, or there's having valid or invalid. It's like, oh, this one exists and this one doesn't, and so on. I should talk about the page replacement. So speaking of those page replacements that we did just now, like the first in first out, optimal and least recently used, to explain it quickly, there's three factors that determines the algorithm. First one is the number of frames on a table, which is the box that you saw earlier. Those are the boxes. The second one is the algorithm, which could be FIFO, optimal, or least recently used. And the third one is the reference strings. So reference strings are the numbers on top that you fill in. So those are the three key factors that determines the algorithm. So three algorithms, upsides, downsides. Let's go. FIFO, it's easy to implement. Downside, it's called a Belady's anomaly. Belady. What this means is there is a anomaly, like it's unexplainable, that like the larger your storage, like the capacity to hold the frames, the more you have, the less efficient it becomes. They don't know what the reason was, but yeah, that's why it's an anomaly. That's one of the downsides of FIFO, and causes more page faults than expected. Next one is optimal. Optimal, of course, is the best algorithm. Like hands, like no contesting. Like, เพราะว่า it sees the future, and that's the problem. We don't know the future, so it doesn't know future. So, no, we don't know future, but if it can, then it would be hands down the best algorithm. Okay, and finally, last one is least recently used. It's better than FIFO, so it might be more complex, but yeah, it's better than FIFO. So there you go. All three algorithms summarized like that. So for diving into least recently used a little bit more, it has like a bit more things to it. They have like what's called reference bits, which are like additional informations that tells you whether or not it has been modified or not. So like it has like ning for being modified and 0 for not yet. Or that, and they have another thing called, they have made an extensions. These are extensions, second chances. So instead of like it instantly killing one guy, just give him another chance. Like, okay, we go look one more further and see if you have another person or not. If not, then you die. Those are like extensions. And then there's also like enhanced second chance, which is combining, it combines both reference bit and second chance together. So what it does, it has 2 bit. Instead of 1 bit, it has 2 bits. So 0 0 0 1 1 0 1 1 to determine the information, like additional information. So like the smaller the bits, it will be replaced, and 1 1, like if it's very recent, then it says don't replace. But this is like the general trend. I don't know where to put this, but just the word thrashing. Thrashing is when you exceed the amount of like efficiency in doing anything in any program. So let's say a computer is like multitask. It's called multi-programming. So no, I program, and the efficiency of it. So like the more tasks you do, and at some point it's going to reach a max capacity, and where the efficiency just completely drops. This is where thrashing occurs. Where when it's full, when the computer is full, it will just stop being efficient, and it will just be continuously swapping things in and out from CPU and main storage. Which, yeah, there's also nothing called allocation. There's equal and proportional allocation. So equal allocation would be giving everyone equal amount of space. So everyone gets like 5 space and stuff. While proportional allocation gives it according to the size of the process. And last term for this chapter is working set model. Working set model is a way the computer sees the reference bits. So just now, if we notice in here, these red numbers, this one is considered like a working set model. There could be more numbers to the right or to the left, but the computer just cut out this amount and sees and organizes it using the algorithm. And then when it's finished with this, it moves on to the next set. That's why it's called a working set. It works on this set first before moving on. Now, we don't know, the computer has to determine how much is optimal. Like it could have like 100 more of these in it as a working set, and that's fine. Or it can have a small working set of like 5 or 2, which it has to balance and figure out which one is optimal for it. So that is working set model. And that's the end of chapter 9. Chapter 10 is storage, like mass. It's called mass storage system. Okay, so in storage, you have to, because the memory is really big, it's kind of difficult to traverse it. And in order to traverse it, there's many methods in traversing. I'm gonna cover each one. First one is first come, first serve. So, well, everything's the same, right? Like first in, first out. So first come, first serve is, yeah, you just go in first. Whoever comes first, it will go to it. So think of the storage as a building. So if it's an elevator, whoever presses the button first, the elevator goes to that guy, and then it will go up to that person, and then it will go to the next person who requests it. But that's kind of inefficient. Now, the good thing about this is upside for it, it's easy. Worse, downside, waste time. Pretty inefficient. Second algorithm is shortest seek time first. This one is the optimal one, like the previous one is. It calculates, it does all the calculations from everyone who presses the elevator and determines which one to take first. So most efficient. So it's the least movement. While the downside of it is, yeah, a lot of calculations. So there's a lot overhead calculation. Okay. Third one is called scan. Now, scan is basically straight up elevator algorithm. So whenever you see elevator, whenever you see scan, just think of elevators. Okay, draw an elevator for you. So an elevator would behave like when it's going down, it passes everyone who's want to go up. So when, let's say, when we traverse, wants to go from floor 8 to floor 1, a guy requests at floor 4, it goes straight down to 1, drops off that guy, and then goes up to 4. That's pretty much it. And it ignores everyone else who wants to go up or whatever until it goes down. When it goes down, finish, it goes up. That's called scan. Next one, sorry, I forgot to write the content. Scan is reduced complexity. So it's less complex than shortest drop first, but it doesn't guarantee the wait time. Okay. So a better version of it comes up. It's called C-scan. C-scan solves that problem by making it calculating the time to make it a uniform wait time. It's uniform wait time. Okay. Excuse me. But the downside for this is, again, overhead calculation, more like overhead movement, say. And so the final form we also use is called C-look. So it's just an improvement from C-scan. That's it. It goes to the last request. It doesn't go all the way down completely like C-scan. That's it. Okay, that's it with Flash. Chapter 11, file system. So organizing. Now we're talking about organizing the files. Oh, this one sucks. There's nothing much to talk about. It's very straightforward. Files are kept in text files, binary files, or numbers. Okay, that's it. You can create files, write files, read files, delete files, truncate files. Okay, that's it. You can access files. Yep. Chapter 12 is implementing it, like taking this, duplicating it, and just implement. How to implement this? So to implement file systems, there's 3 types of file allocation. Now, this is not like process allocation. This is files. Okay. So we're dealing with big information, not small ones. We're looking at a bigger scope. So there's 3. First one is contiguous allocation. Contiguous allocation. What this does is it compacts everything. It accesses all the files in blocks, basically. So if this is your block, then when I access it, I can just access this one zone. I don't have to access the entire thing. That's contiguous allocation. Second one is linked allocation. Linked allocation is like linked list. You can keep your files anywhere in the storage, and each one will just point to each one. So when you access this one, you can just jump. Upside downsides I'll talk about in a bit. And index allocation. Index allocation is you have a table that points to the stuff inside. So you just look at this and say, okay, these guys are here pretty much. Upside downsides, contiguous, best guy, best. Most cases at least. And it's good for sequential and random access. However, linked list is good for sequential, but not for random, because it's all in order, you can see. While index it's more complex. I can't say the upsides, just say it's more complex. It depends for index allocation. Okay, you have it. Next one, chapter 13. Blech, another nothing. It's just I/O system. I/O system is basically like your mouse. Whenever your mouse wants to click, it has to tell. There's two ways of your computer knowing what to do or what not to. So first one is called polling. Polling is where the CPU asks, like, it's a keyboard, do you want to type? Ask the mouse, do you want to click? Do you click? And it has to keep on asking, depending how many times you want it to repeat. But it will continuously ask the devices. The second one is interrupt, which is much better, where whenever the keyboard wants to type, it just lets the computer know, like, hey, I'm going to type. You stop everything first. Give me space. click, give me space. Okay? That's interrupt polling. Moving on. And then there's a way for like called direct memory access. It bypasses the waiting time, just directly access stuff. Chapter 14, protection. Chapter 14 is how to protect. Well, best way to protect, there's many ways, but one of the main ways is access matrix. So in this code, you have permissions and roles, right? You have to assign roles, and only some people can have access to some things, while some other people don't have access. That's it. So like a circle, right? Both of you guys can read the text files, but some people, like let's say admin, they can read, they can write, or they can whatever delete, while let's say like an intern can only like, I don't know, smile. Yeah. So these are domains, and the amount of access are limited. That's it. Last chapter, 15, security. Those of you who have taken cybersecurity courses, that's it, bro. That's it. It's CIA. Try it. Confidentiality, integrity, and availability. All three of these, don't breach it. If it breaches, then your computer's screwed. Noteworthy concepts for security is masquerading. Masquerading is disguising, pretending to be someone that you're not. And logic bomb. Logic bomb is waiting for someone to touch it. It's like a trap. Whenever a certain condition is activated, it will go off. Keystroke logger is it logs whatever you're typing. Cryptography. What's the difference between cryptography and encryption? Well, I don't think there's any computer. I'm gonna explain. Cryptography is how the person, the sender and receiver, how do they talk? What channel do they use? How secure? Like what kind of secure channel do they use? Encryption is the message itself. That's it. That's all of OS that I predict. I might miss some, but